Okay, welcome back reinforcement learning. This section I explain the distributional Q learning. Okay, we are seeing the last session the distributional Bellman equation we are using in distributional Q learning to predict the distributional uh, distributional expected rewards. The distributional Q learning, we have the two important parts in distributional Q learning. The first one is representing a probability distribution in Python. How to represent the probability distribution values in Python. The next one, it is the distributional Q learning. It is with the probability distribution of rewards and implementing the distributional DQN. Okay, these two are the key concepts in this session. The first one is representing the probability distribution in Python. In probability distribution, we need the two arrays. We need the two arrays. The first one is the support array. Second one is probability array. The support array, it contains the possible outcomes. Support array contains the possible outcomes. For example, support of the distribution. It represents the range of values in the rewards. The rewards range of values we are represented. That is the support array. For example, we have the range of values -10 to 10, plus 10. We create the support array with the evenly spaced values within this range. Next one is probability array. The probability of rewards. This array holds the probability associated with each outcome in the support array. So these two are the arrays we are representing in probability distribution in distributed Q learning. One is the support array, second one is probability array. Okay, in implementation of the probability distribution, the first one is we setting up the support array. The support array it has a supportive possible outcomes. So you define the minimum and maximum value of the support values and specify the number of elements in this range. So for example, we have the minimum and maximum -10 and +10. The number of support values is 51. So we first setting up the support values in implementation of the probability distribution in Python. The next one is creating the probability distribution. Each outcome probability we are calculated. So initially initialize the probability array with equal probabilities for all outcomes. For each support element the equal probability initially. And next one is normalize the probabilities to ensure them sum to 1. The probability distribution, sum of the probability distribution must be 1. So we normalize the probabilities to ensure them to 1. So the probabilities is np dot ones and probabilities probability by the normalize the probability distribution values. Next step, visualizing the distribution. After probability distributions are calculated of the outcomes, we are visualizing the distribution by using matplotlib to visualize the probability distribution. So we are using bar charts for the x labels and y labels and title. We display the plotting using matplotlib for the probability distributions. So if this is the example code for the probability distribution in Python, the first one is define the support values and create the probability distribution and visualize the distribution. By representing the probability distribution using NumPy arrays, we can effectively model the uncertainty in rewards within the framework of distributional Q learning. This representation allows for more nuanced decision making and learning in reinforcement learning environment. So the distributional Q learning, the next concept is implementing the distributed DQN using distributed probabilities. So distributional deep Q network is an extension of the traditional deep Q network DQN. It is the extension of the traditional deep Q network that model the distribution of the returns rather than just the expected values. We have the multiple distribution of the expected values. This approach allows the agent to capture the uncertainty in the rewards, learning to improve the performance in reinforcement learning. In this architecture, in implementing the distribution DQN, we have the architecture, we have the neural network architecture is the first one is input layer, hidden layer and output layer. The input layer, DQN accepts the state represent the input to the input layer. The state is the position or velocity of the game. These are the state of this, these are represent the state of the environment. Okay, in this implementation, in this example, we are using 128 element state vector is used which represent the various features of the environment. The next one is hidden layer. Hidden layer is the receive the input from the input layer. The state vector is passed through the series of fully connected dense layers. These layers learn to extract the relevant features from the input state. So the hidden layers finally we give to the connected to the output layer. The final layer produces the three separate distribution vectors, each corresponding to a different action. So each distribution vector represents the probability distribution for the possible returns of the actions. In this example, the output is structured as a 3 into 51. So the 3 represent the number of actions and 51 represent the discrete support in the distribution. We take the 51 ranges. So the softmax function we are using for the probability distribution. This is the output layer architecture. Next, in implementation steps, define the neural network. The first one, create the neural network architecture using the deep learning framework, either PyTorch or TensorFlow. We are using the PyTorch. The network should consist of the input layer, hidden layer and output layer as described in above architecture. And we apply the forward pass, implement the forward pass of the network, which takes the state vector as the input and produce the output probability distribution matrix. Next one is we are calculated the loss. Loss is the difference between the predicted values and actual values. We define the loss function that measures the difference between the predicted distribution and the target distribution. Common choice include the Kullback, Leber divergence or Washington distance. And training this loop, the implement the training loop where the distribution is updated based on the observed rewards and the corresponding target distribution values. Based on that, we train the model to reduce the loss. The example code, the first one define the neural networks, and next one is forward pass. The next one is train the distribution, collect the experience and compute the target distribution and update the model. We collect the experience, gather experience tuples, state, action, reward and next state from the environment and compute the target distribution and update the model in order to reduce the loss. So this is the implementation of the distribution. DQN allows for a more nonlinear approach to reinforcement learning by capturing the distribution of the expected returns. This leads to improve the decision making and performance in complex environments. By following these outline steps and utilizing the provided code, this practitioner can effectively implement and train the distributed DQN for various reinforcement learning tasks. So thank you.